Hello, everyone, and welcome to the Introduction to EMM Science Data session. I'm just going to give everyone a few minutes to just join. All right, people seem to be joining. So I think just going to go ahead and share my screen here. All right, so I would just like to welcome everyone once again to the Introduction to EMM Science Data virtual session. In this session, you'll basically learn about the 3 scientific instruments on board the HOPE probe and their observations and data sets. So if you plan to use EMM data, this session is definitely for you. It will provide you with the understanding and the confidence in accessing, navigating, and handling the data sets as well. Just to remind everyone that these sessions will run from 7 to 8:30 p.m. UAE time. By the end of the session, if we do have some questions coming in from the attendees, we might be able to go a bit over time to answer all your questions. And also, if you do have any questions, please feel free to leave those in the Q&A box. So we will not be unmuting anyone's mics to ask questions, but you are free to ask as many questions as you like in the Q&A box. So just to go through the agenda real quick for today. So we will first begin with an EMM overview, and we'll go through a presentation on the Science Data Center, the Emirates Exploration Imager, the Emirates Mars Infrared Spectrometer, and Emirates Mars Ultraviolet Spectrometer as well. So without further ado, I believe we can start off with Hassa Al-Madroushi with the EMM overview. Thank you very much. Hassa, you can take that away.
Thank you, Moza. Can you confirm that my screen is on?
Yes.
All right. Hello, everyone. This is Hassa Al-Madroushi. I'm the EMM Science Lead, and I'm here to give you a very quick and brief status about the Emirates Mars mission. So I would like to give you a quick glance on the timeline of the Emirates Mars mission since launch. As you all know, we launched last summer in July 2020, and we launched from Japan at the Nagashima Center. And the whole probe went into a journey of 7 months cruising until we arrived to Mars the beginning of this year in February 9th, 2021. When we were captured in Mars orbit, we were at an orbit of 1,000 kilometers by 42,000 kilometers around that, and around 19.5 inclination, and the duration of the orbit at that time was around 34 hours. We stayed there to do calibration activities for the instruments and checking the health of the spacecraft and its system. And after that, we went into transition to science orbit. So we moved into our scientific orbit, and this is how it looks like. So the dimension of it is 20,000 kilometers by 43,000 kilometers. So it's wider to enable the size of the mission to be achieved. It has a 25 degrees inclination in addition to a duration of 55 hours. So that's the time that the whole probe takes to complete one orbit around Mars. After that, we began our science phase, and that was officially the end of May 23rd, 2021. And we will stay in our science phase for 1 Martian year to study the Martian atmosphere in all its season, and that equates to 2 Earth years. And we reached in this month an important milestone, which is the release of our first data sets. And that was on October 1st of this year. And during the first batch of the data release that we have in the science data centers, we had all the data that the probe had taken since Mars orbit insertion, so since February 9th, until a day before the science phase began, so until May 22nd, 2021. A reminder to everyone about the science of the mission. So we do have 3 scientific objectives. Objective A is about characterizing the Martian lower atmosphere. This is where we're looking into the temperature, we're looking into ozone, water ice, water vapor, as well as dust activities in there. Objective B is more about correlating the conditions of the lower atmosphere with specifically the escape of hydrogen and oxygen, which are the building blocks of water. And then objective C is about characterizing the exosphere. And the exosphere is the layer where escape happens in. And as I mentioned, we're looking into hydrogen and oxygen specifically in there. And I would like to mention, while we're linking between the lower atmosphere and the upper atmosphere, specifically the exosphere, we're studying the thermosphere layer, which you can see in the graph in here, where we're looking into oxygen and carbon monoxide. To achieve these objectives, we do have 3 scientific instrumentations that you will hear more in details about. We have the Emirates Mars Infrared Spectrometer EMERS, developed by Arizona State University and Mohammed Barash Space Center. We have Emirates Acceleration Imager EXI, developed by Laboratory of Atmospheric Space Physics and Mohammed Barash Space Center. And we have Emirates Mars Ultraviolet Spectrometer EMUS, that is developed by LAOS and MBRC as well. When it comes to the science of each instrumentation, so first we have the EMERS instrument. This is when we're looking specifically in the lower atmosphere, and the EMERS instrument will give us scientific projects that includes the temperature profile. So we're looking at atmospheric temperature, surface temperature, the dust optical depth, the ice optical depth, as well as water vapor. Complementing EMERS, we have EXI looking as well into the lower atmosphere, giving us information about ice as well, and ozone, as well as beautiful images of Mars and using the 3 bands of red, green, and blue. Then we have the EMUS instrument, which is looking specifically at the upper atmosphere of Mars, which is the thermosphere and the exosphere. So looking at the exosphere, we're studying the density of hydrogen corona and getting the density of oxygen corona. And in the thermosphere, we're looking into the relative column density of oxygen and the relative column density of carbon monoxide. So information from these 3 instrumentations work hand in hand together. So we understand the different layers of the atmosphere as in different seasons and with the diurnal variation. So we're looking to day to night variations within the subseasonal variations as well for one full Martian year. And that kind of perspective enhances our understanding about atmospheric dynamics. The Emirates Mars mission is the only mission right now that is capable of giving us like this comprehensive view of the atmosphere, where we have global geographic coverage as well as local time coverage with diurnal variation inside. So you can see in here like the orbit that we have around Mars. As the whole probe is moving around the orbit, we have here views from EXI that can show you how we are viewing Mars as a whole. So we have this kind of synoptic view, and we're able to look at the different times across the day while looking at Mars and orbiting around the planet. I would like to highlight that the Emirates Mars mission is a result of international collaboration. This mission is funded by the UAE Space Agency, carried in implementation by Mohammed Barash Space Center, while having 3 academic key partners, which are LAS, Space Science Laboratory, SSL, and Arizona State University, ASU. And that would be a wrap up of my presentation. If you have any kind of question, I would be happy to answer them through the question and answer box. Thank you.
Thank you very much for the wonderful introductory presentation on the EMM overview, Hassa. Now we'll have Brian present the presentation on the Science Data Center.
Hello, everybody. So my name is Brian Harder, and I'm one of the leads of the Science Data Center. I work out of University of Colorado at the Laboratory for Atmospheric and Space Physics. So what is the Science Data Center? So in short, we're the central repository for all of the data on the mission, all of the science data. On the right-hand side there, I have a little diagram of where the Science Data Center sits with respect to the rest of the ground mission. The ground operations on the mission. So we'll receive the raw telemetry from the spacecraft, and we have 3 jobs at that point. And one is data management, managing all of the data, storing it, backing it up, indexing it, taking that data and processing it from level 0 files, which is the lowest level of processing, to level 1 and level 2, which are higher levels of processing, which I'll talk about a little later. And then 3, disseminating that data to both the science team and the public. And the primary way that we disseminate that data is through the website, which I'll walk through a little bit later. And then just an interesting tidbit about the SDC is that it's actually physically located in Ireland. And that's because it's hosted entirely using Amazon Web Services, which is a cloud provider. So what type of data do we have at the Science Data Center? So first of all, we have data for all 3 instruments, EXI, EMUs, and EMIRs. Right now we have level 1 data, which is typically uncalibrated. The levels refer to how processed the data is. So level 0 is basically the packet files that we receive from the spacecraft. Level 1 is raw data. It's uncalibrated and it's usually not used for science. Level 2 data is the next level up of on the processing chain. At that point, the data becomes calibrated. It starts using physical units. Things like geometry are added. This is the typically used data level for doing science. Beyond level 2 are level 3 data, which are not yet available at the Science Data Center, and that's by design. That'll be released in a couple of months. I'll go over the release schedule in a later slide. And that'll contain derived quantities. What's physically in those files will be determined by the different instruments. So level 1 to level 3 data, that's all, everybody uses the FITS file format. If you're not familiar with FITS, I have a little link here, but it's a pretty standard file format used in astronomy. At this link here, they have different readers and such. And finally, we also have quick look data files. These are not FITS files. These are actually just PNG images that you can use to quickly download the data and take a look at it using any sort of photo browsing app. So in addition to the actual science data from the different images, from the different instruments, we have these SPICE files and an associated metakernel for them. If you're not familiar with SPICE, what that describes is the geometry of the spacecraft. So it'll show, it describes the position of the spacecraft and the orientation of the spacecraft, as well as its different instruments with respect to Mars, with respect to the solar system. The SPICE files are a whole library that's developed by JPL. There's a link here to get you started on SPICE if you don't know much about it. But that being said, it shouldn't be super necessary to do science because a lot of the position data is located within the science files themselves. Also on the Science Data Center, some software to help search and download data from the Science Data Center, as well as documentation for using that data, as well as the software. So let's take a look at what the files look like when you first look at them, what the names look like. So I think you'll see this slide from each of the different instruments as well. But what this is describing is how the files are named. So each field here in the file name is separated by an underscore, and each field represents something else depending on the order it shows up in the file name. So every science file begins with the letters EMM underscore. The next 3 letters represent the instrument. The next field represents the data processing level. So how far up in the processing chain is it? The date and start time of the observation. So that's the start time, not like the median time or anything like that. This is when the data in the file starts. Likewise, the orbit number, that's when the data in the file starts, which orbit number that is. The next 2 fields are the mode and the descriptor. These fields are both optional. Different instruments have different observation modes, and they can feel free to put that in the file name located here. And then any other relevant kind of descriptors that are needed to understand what's in the file are in the next field. Every science file also has a field. This is just a singular letter that indicates whether or not the geometry located in the file is preliminary, reconstructed, or it's final. The geometry will no longer change. And then it ends with 2 numbers here, 1 for version and 1 for revision. So you can see, as the pipelines for data processing get more refined, these version numbers and revision numbers will go up. So typically we only release the latest versions and revisions to the public. And then also I just added this .gz here at the end. Some of the files are in a gzip format, while others are not. Usually for any FITS file reader, they can read gzip files or non-gzip files just fine. So it should be transparent to the users. And then I just have examples of the different file names that could be, that you could see on the Science Data Center down here. So let's take a look at the first one. The first one, EMM, it's from the instrument EXI. It's a level 2A processed file. It starts, what is this, March 2nd, orbit number 15. And this says it's an observation type XOS4. You'll hear more about that later. This is a descriptor that EXI uses that shows the frequency of the data that they collected. The SPICE processing level, so this is a reconstructed file, and then it's a version 2, revision 2. And then similarly for EMIRs, it looks pretty much the same. They don't use any sort of descriptor or mode fields generally in their science files, and that's perfectly acceptable. They only have the one observation mode. Okay, so what time range of the data is released? So as Hessa already said, the data that's available right now is level 1 and level 2 data that's from the start of MOI, Mars Orbital Insertion, to the start of the nominal science phase of the mission. So that is February 9th to May 23rd of this year. On the chart on the right-hand side here, I have a little handy visualization of what data sets will be released when. So each line here represents a year. Right now we're at October. We're in October, and at October 1st, data set number 1 was released. So it's color coded here. So data set number 1, level 1 and level 2 files for the transition period of the spacecraft. That's all been released. So with the next release, releases occur every 3 months. So the next release will occur January 1st, and that will contain the level 3 files from the first data set, from the transition period. In addition, that release will also contain the level 1 and level 2 files for the first 3 months of the science phase of the mission. So extending from the end of May to the very end of August. And then the releases at that point are staggered. So every 3 months, you'll see level 1 and level 2 data from the previous like 6 to 3 months, and then you'll see the level 3 data show up from the previous 9 to 6 months. And that continues on for as long as the mission is operational. Okay, so the EMM website, this is how you'll primarily interact with the data, most likely. So you can find the link here. If you plan on accessing the data, you need to create an account. It's really fast to create. It only requires your name and email address. And really, it's only required, 1, so that if you make a large download request, we can send a link to your email and you can download it that way. And 2, we just want to ensure that it's not constantly being bombarded by web crawlers. So really, we don't do a whole lot with your registration with your email. You optionally have the you can optionally sign up to receive emails whenever there's a new data release. But other than that, you don't get signed up for any other sort of email list. So that being said, I'm going to, instead of going through these slides, I'm just going to show you real quick the Science Data Center. So I'm logged in as a public user, and we'll just take a look or poke around the data center. So this is the home page. This is the only page that can be accessed without an account. For accessing the data, you'll want to go to the Science Data Search tab. So Science Data Search, We can select a date range here. Every search requires a date range selected. So let's just select these 2 days here. If you scroll down, you can select which instrument you'd like to view the data for, what data processing level you'd like. So let's look for quick look data. Data version. So this says, do you want to search all versions of the data, or do you only want those latest versions and revisions shown? Generally, you'll just want the latest. There's not very many scenarios I can think of where you'd want all of the data. And then we have a few other search parameters here. You can search by spacecraft latitude, longitude during the observation, altitude during the observation, as well as local solar time during the observation. So you can narrow your searches down further here. So let's just go ahead and search for data here, and I'll show you what pops up. So you get a giant table here of the different files that were found. So you can see about 360 EXI quick look files were found for these 2 days. If you want to download these files, you'd select that, which ones you'd want downloaded. If you select only one file, what you'll get is a link to just a singular file. If you want to download multiple files, it'll go ahead and provide a tar file for you. You'll download that, and you can see it's creating a tar file for me. So if you unzip that tar file, you'll see the data that you selected in there. For really large data queries, like if you go ahead and select all of these, even this actually probably won't trigger it. But usually when you start downloading in the gigabytes of data, what it'll do is say, okay, we need to take your request and put it into a queue. We'll zip it all up for you, and then we'll send you an email with a link to the data. So that is how you use the website to download the data. I'll go into a few different methods in a little bit. The ancillary data search page, this, we're going to add a few more filters in the future, but right now the only thing we have is the start date, end date of the ancillary files. There's only 160 released. The ancillary data is really just 2 types of files. One, the SPICE files that describe the geometry of the spacecraft, and 2, there's some events files that you'll see in there. The events files are just these XML files that describe when certain events happen with the spacecraft, things like periapsis or solar conjunction, things like that. These links down here, primarily what these links serve as is documentation. So you go to the EMURS page, you'll see the EMURS data products guide. If you go to the EMUs page, you'll see the data products guide and a few other pieces of documentation they'd also like you to see. If you click get the latest EMUs data, it'll just take you back to the science data search page with EMUs selected. So what else is here? So there's a data availability chart. So this just shows a month view. And in each of the different days here, you'll see a different box that says, okay, what's the highest level data that we have for the different instruments? So you can see, this day in April, there wasn't any data from any instrument. And this day has EMUs level 2A, EXI level 2. As we get further into the mission, I expect this will be filled in a little bit more. But this was still early in the mission, so things were still a little bit in flux. So you can also filter by, what data level and instrument you'd like to view. The quick look page. So as I mentioned before, EXI and EMIRS both have quick look files, which are just PNG images of their observations. So we have a quick look browser here for the EXI data, and the EMIRS quick look browser is coming soon. And you can go through the different dates here, look at the different frequencies of the data, and you can scroll through and see, there you go, there's pretty pictures of Mars. So there's just some data here about the different files. And if you want to go ahead and download the level 2A, level 2B data related to this image, you can click find related data and it'll send you straight to the Science Data Center download page with that data all filtered. Okay. So what else? So we have software on the Science Data Center. So if you want to programmatically access the data, obviously the website itself, clicking the buttons manually isn't going to do that. We have APIs that you can hit that will query for certain data, download data to your files without needing, or download data to your computer without needing to go to the website. So we've created two different software scripts, one in Python and one in IDL. And these are pretty simple scripts, but they kind of abstract away the complexity of the API. And you can use this to query and search for the data. So in another tab here, what I have is just a quick demo of what the Python download script looks like. If you're familiar with IDL, these commands will look very similar. But basically, there's just a few functions inside the Python script file. I'm going to import the API. This is a Jupyter notebook, by the way, for those not familiar with it. This is just essentially a Python script that I can execute one line at a time, just for easier visualization of what I'm doing. Okay, so import the EMM API. I want to query for science files. So in this case, what I'm doing is I'm saying, okay, I want the EXI instrument for this start date. Level, I want it to be QL, which is quick look. Observation mode, XOS1. And furthermore, I want to narrow it down to just times around local noon. So if I go ahead and click that, all right, I need to log in. So it'll prompt you to log in. Let's see. At which point, so this is just the username and password that you signed up with for the Science Data Center. And you get an output, a big JSON file describing exactly the type of files that you queried for. So the first thing here just describes, okay, here's the file that you found, here's the directory. It's, an EXI file, quick look, blah, 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 all this other stuff that we have that's associated with that file. And then if you actually want to download it, it's basically the same filters that we had before, but it's using the command search and download. So you can just click that. And as you can see, it's starting to download the files to my computer. So we can actually go in and see. There we go. Mars starting to be downloaded. Oh, that's just a thumbnail. There we go. Okay. Let's see, what else did I want to say? So like I said, these Python and IDL scripts, they just wrap around an API that we've made available. The details of it are a little bit complex, and that's located, the documentation for that is located also on the software page. So if you open that up, there's documentation about how to use that API, not using the Python and IDL scripts. So if you want to create your own scripts that query the data in some specific way, or using a language that's not Python or IDL, you can reference the SDC API documentation here. The API keeps track of a bunch of different parameters for each observation type. So on the software page is just a list of all the different parameters that you can query for to help filter and download the data. So we have things ranging from, okay, we've got what instrument do you want? What level do you want? What mode is that file? And then we also have a few geometry parameters, spacecraft local solar time at the start of the observation, the Mars season, spacecraft altitude, etc. So the full list, like I said, is under the software tab there. The publication and links are currently blank, but these will be filled out as the mission progresses. So that is, I think, all I wanted to mention about the Science Data Center. So going into the future, just in the near future, what we have is we're going to develop the EMIRS Quick Look Viewer. So you'll see something for EMIRS, similar to what you saw for EXI. EMUs will also have quick look files. Currently, they don't have any on the Science Data Center, but when they are available, we'll make a quick look viewer for those. We plan on having more advanced searching and filtering on the quick look page. And then we also hope to have more filters on the columns of the data search tables when you search up specific files. And then finally, I just wanted to end it with, if you have any suggestions or you need any help or questions, we're happy to help. And in fact, in some cases, incorporate requests into the website, into the capabilities of the Science Data Center. Our email is located at the bottom of the page of the Science Data Center website, so feel free to contact us there. And that is all I had.
Thank you very much, Brian, for the informative presentation and taking us on a walkthrough on the Science Data Center as well. Before we move on to the next presentation, I just want to remind everyone that if they do have any questions, to leave those in the Q&A box for the team to answer. And now we can just move to the next presentation. We'll just shuffle things around for a bit and move to a presentation on the Emirates Mars Infrared Spectrometer by Christopher.
Okay, I hope everybody can see and hear me. All right, so my name's Dr. Christopher Edwards. I'm a professor at Northern Arizona University and the EMIRS instrument scientist. And so today I'm going to talk to you a little bit about the EMIRS instrument and what you can expect when you start looking at EMIRS data. So EMIRS is an interferometric spectrometer. And so it is it has a tiny little mirror inside of it that moves back and forth and creates constructive and deconstructive interference. And that's actually how we measure the different wavelengths of light. And so similar instruments to this have gone to Mars and actually all over the solar system on previous missions. And EMIRS is kind of the next evolution of that instrument. And then it combines many of the technologies that were independently kind of created for those missions into this this new instrument. And so EMIRS was developed jointly by Arizona State University in collaboration with Mohammed bin Rashid Space Center. And some of the innovations that we have here, EMIRS has a smaller field of view, which enables relatively small footprints from large distances like the EMM orbit. We have this high spectral resolution mode, this 5-wave number mode, and a broad spectral coverage from 6 to 100 microns. If you want some additional information, I've posted the reference here for the EMIRS instrument paper, and you can just click that link down there, or you can copy down that link down there at the bottom, and that'll provide you a bunch more information about how this instrument actually works. So EMIRS plays this role on the mission, as you heard Hessa talk about earlier, kind of providing key information on the 3D structure of the lower atmosphere and its variability on subseasonal timescales. And so not only do we provide these temperature profiles, we actually provide information on some of the key atmospheric constituents. That would be things like the dust optical depth, the ice optical depth, and the water vapor column abundance. And so we provide surface temperatures, temperature profiles, and all these other things to the mission that can then be linked up to and with the other instruments due to the unique observational strategies that EMM employs. Here's just an example of what some of these spectrum that you may see look like. So on the top here, this is just a radiance spectrum, and it's superposed on top of just different surface temperature spectra. Down here, once you convert this radiance spectrum to temperature, you can see that some unique things start to pop out. and there's a nice big CO2 absorption feature. This out here at longer wavelengths or lower wave numbers is water vapor. Around here is water ice, dust, and here's approximately where we derive surface temperature from. So EMIRS, it has all of these spectral data that you can really play around with to get at unique properties. Here's what the two observation strategies look like for EMIRS. So EMIRS has two different strategies. One is a 10 wave number mode sampling, or a lower spectral resolution mode, and a higher spectral resolution mode. In the lower spectral resolution mode, we get better coverage on the planet and are able to retrieve these parameters that I was talking about all very well. The biggest difference is between water vapor between the two modes. And so in the ROS1 mode, which is the 5 wave number spectral sampling, the higher spectral resolution mode, you'll notice that the spots on the planet are a little bit further spaced out. And the videos that you're seeing here correspond to the different altitude bins as we go up. So EMIRS has kind of different acquisition strategies depending on what altitude the spacecraft is at. And this is just an example of what these spots look like with time. So in general, we don't actually differentiate between these modes. You can get all of this information in the header data. And so here's what a typical EMIRS observation looks like. EMIRS uses this internal internal calibration target and a space looks to calibrate the data. We have less than 300 kilometer per pixel spatial sampling. We acquire approximately 20 observations per orbit, although that depends on the available data volume. And the different acquisition patterns take between about 30 and 10 minutes at the different altitudes of the EMM orbit. So EMIRS has a couple of different data levels that I wanted to describe really quickly. So Brian did a great job of talking about these in general, but EMIRS has some kind of special things that are worth mentioning. For the level 0 products, essentially nobody will ever use these products. They are complicated to look at. Level 1A and level 1B are when things start to get really interesting. And so level 1A is just the raw interferograms and housekeeping data that come back from the spacecraft and the instrument. And there's one FITS file per observation. Level 2 or level 1B are basically once we start running the data through the processing pipeline, you can then start to see a spectrum. However, that spectrum is going to be completely uncalibrated. Level 2 is the calibrated radiance spectrum, and this has all of the geometry information. It has some brightness temperatures. Quick look products are produced from this. And we see one FITS file and one set of PNG or quick look files per observation. And so the level 2 products are probably the most useful things that we release at this point. Level 3 are not released yet, but these will be after they've gone through our retrieval algorithms to get at the surface temperature, emissivity of the surface, water ice, water vapor, dust opacity, and atmospheric temperature profiles. These will also have one product or one FITS file per observation, but then we'll actually take many of these FITS files and combine them together so that they're binned on local time. So you can get the data that were acquired over the last week from let's say midnight to 3 a.m. if you really care about that, for example. So I highly encourage you as well to take a look at the data products guide that Brian mentioned. There's lots of stuff in here. Here's an example of kind of the ancillary data that we have at the end of this. So we've basically gone through and shown what fields are available in what data products. And so there's also a nice description of what these are. And there's about 200, I think, of these different fields. So I'm not showing you all of them, but it's something to definitely go take a look at if you're interested in using these data. Just again, to give you a sense of that flow. So right now we are are talking primarily about this level 2 processing pipeline and quick look generation. And then we also have this level 3 processing pipeline that is produced at the instrument team facilities. And so right now, all of the data that are released are being run and processed at the SDC and delivered that way. And eventually, in January, these new products will be pushed up to the SDC and will be available for release there too. So you saw this already, so I'm not going to belabor it, but one of the big things to pay attention to with EMIRS is the data product level. So you want to look for level 2 and or level 2 quick look. And then we have this type of kind of science product that we have available. So we have surface temperature, atmospheric temperature for the quick looks, and then there will be interpolated versions of both of those. So there are 4 different quick look products that you can take a look at. And here's an example of what those quick look products would look like. So here's the interpolated version, and here's as the instrument kind of acquired the data. And here's again another version of the surface temperature. And this is actually just for fun. This is the first image that EMIRS took of Mars. So it's pretty fantastic to see this. In the last couple of minutes, I wanted to spend just about 5 minutes talking about JMARS. You maybe saw this on the data product page, on the SDC page that Brian mentioned. So JMARS stands for the Java Mission Planning and Analysis for Remote Sensing. And it's a tool that is used by the EMM team for visualization and has been developed over the last 20 years at Arizona State University. It's used widely across missions for Mars, asteroids, the moon, Earth. There's basically a JMARS for everybody, or everybody that's had a spacecraft go to it in the solar system. Currently, JMARS has all of the publicly available EMIRS data available for use, and I'll walk you through what that looks like. And soon, JMARS will have EXI and EMU's data products as well. Where those different layers, as you'll see, it kind of acts like Photoshop in that way, that you can reorder the layers, are in progress. And yeah, just kind of like the quick look pages for EMIRS, we expect to see those in the next couple of weeks. So again, just go to jmars.asu.edu to download this. You should create an account as well, and but you have all available, all of the data that are released, at least for EMIRS right now, in the JMARS tool. So you have multiple ways to interact with EMM data in JMARS. For EMIRS specifically, since that's the one that's available, I'll talk to that mostly. You have the ability to query the data by pixel. So we know that EMIRS takes data over many local times, and just kind of this complicated set of observational geometries. And you can say things like, I want only the data between 3 a.m. and 5 p.m. for this time when it was acquired, with these parameters, et cetera. And so you can use the acquisition parameters, say when a detector was warm or cold, or whatever you want to do. And then JMARS returns these data to you, both allows you to visualize them kind of in real time, so you see what query you get, rather than going through tens or potentially even hundreds of individual FITS files. You can use this tool. And then allows you to export these data as well in common formats such as like CSV. When we have level 3 data released, JMARS will have some kind of pre-canned products as well. These would be like regridded, the regridded products I was talking to you about before. So every week or so, EMIRS is going to create these binned products where they're basically global maps of data acquired over 3 a.m. to 6 a.m., 6 a.m. to 9 a.m., et cetera, et cetera. And so those will also be available in JMARS as well as on the SDC. So here's, for example, what you would want to look at with JMARS. So you'd see these, you pull up a new layer here, you search for EMIRS, and you say, oh, I want to pull in the EMIRS spots. And you can set latitude, longitude boundary. You can have all of these different parameters that you may care about. There are basically any parameter that is available in the FITS file is available here if you were to scroll down a little bit, you'd see add advanced parameters, but we kind of highlight some of the most useful ones. Once you do that, and we just did a simple query here, you could see, here's where all of the spots for emitters would fall given this specific query. Those data, if I then zoom in, you can see there are individual spots. And so if you highlight one of these spots, you can actually then see that you can actually pull the raw calibrated radiance spectrum from that individual spot. And so that's great because you can very easily start to look at these data, and then you can actually go ahead and export these data as well. JMARS also has this nice 3D view that you can see too. So you can spin this globe around over here and get a sense for the geometry that the instrument was observing Mars. And that is all I have to talk about emitters.
Thank you very much, Christopher, for sharing this wonderful presentation on emitters and taking us on a walkthrough in JMARS and how we can be able to visualize the data as well. Based on that, I hope a few of the attendees do have some questions with regards to that. And if any of the attendees do, please leave your questions in the Q&A box, and we'll be happy to answer those for you. Next, we'll have a presentation on the Emirates Exploration Imager by Michael.
Hi, everyone. I'm Mike Wolf. I am the EXI instrument scientist, and you've had a couple of excellent presentations already that will give more context to mine, which is great. You never know when you're putting these slides together how much background you need. So that will make some of these slides a little easier to understand. Let's see, okay, so as with the other presentations, there are some background materials that you'll find very helpful and provide nice context for your exploration of the EMM data set. The first is the instrument paper. It is still currently in press, and I don't have a DOI number for you that works. But from what I can tell from the SDC website, as soon as that is available, this document or a link to it will be available at the SDC website. But what is there already is the EXI product guide, which would be an excellent place to start in terms of exploring the data, various assumptions that are used in calculating quantities that you'll find in the file, etc. So it's a very good reference document, the second one. The first one is more of a high-level overview, or if you're really interested in very low level, like the optics diagram or the electronics block diagrams, you might see some of those there. So, but some background information on EXI. There's a finite element method or finite element display on the right there. It sort of shows you the construction. EXI consists of two telescopes, one for the UV and one for the visible. And that's simply a function of the optics. It's hard to get a single set of optics that does a good job over the full range of the filters. And the filters that are involved you can see off to the left here. 3 UV and 3 visible. Now I hide the three blocks there show you numbers that are out of spec. In other words, the 220 response did not come about in a way that we had hoped, nor the 260 also had problems. And so you need to be careful using these, and there's where the instrument paper will be a little more helpful. You need to really understand what these band passes are. The 220 was originally specified to be able to provide sensitivity to dust in the Martian atmosphere. Because of the problem with the filter, it's so wide now compared to what we needed. There's almost no sensitivity to the dust. And for the 260, the idea was that's the ozone band that's sensitive to ozone. But there was again an issue related to the function of the bandpass. And in this case, it's what is the out of band rejection for visible light is not quite what we needed. And we are working on a correction for that to recover some of the capabilities. But if you thought you were going to go use this right away to look at ozone in the Martian atmosphere, there are some sensitivity issues. So just those are kind of warning. The other four are working great. And actually these other two are working great. It's just the specification. It's not quite what we had hoped. So speaking of that, just how great is great. So the radiometry is actually quite good. So the 320 and the 635, the ones that have been most heavily analyzed so far, our radiometric precision is better than 5%. And this is awesome for imaging. So lots of good work can be done. The other two visible channels are still under analysis, but there's no reason to think that they won't be as good as the 635 or the red filter. The two UV channels that I warned you about, there's a little more breakdown. I mean, the 220 is actually well calibrated. The problem, as I mentioned before, is it doesn't quite do what we wanted. It's too wide, and so the dust signal is swamped in all the other radiance there, and you really cannot do dust retrievals as we had hoped. And then for the 260 for the ozone, there's sort of our quantification of what is the uncertainty there due to the red light or visible light coming in to the UV signal. It's about 10 to 20% uncertainty. We are in the process of trying to correct for that, but essentially what you need to do is have an idea of what's happening in the visible, and with our visible bands we can, and then construct a wavelength dependence and then calculate how much of that light will be there and then subtract it. So it can be quite complicated, and at some point we'll be there. So what are these different types of observations? So off to the right is kind of a schematic about the normal science operations. XOS1 is the primary science mode for EXI, in that it takes all 6 filters, but they are binned to some degree. 2x2 binning with those triplets that you see there, the 2 UV images and the red, and then 4x4 binning for the blue and the green. And there's some dark images, and then there's a second set, which is probably kind of strange. Those are binned 16x16, and the idea is to capture places on the planet observed by emirs, which happens between these two sequences, but were not present when we did the XOS1, or they were extreme on the limb. So pixels rotate into view that weren't there originally, or maybe in a better geometry. That's what the XOS2 is for. And the reason we can get by with the 16x16 binning is that the emir's footprint is still fairly large. So that still gives us quite a few pixels per emir's footprint, which is its goal. Of course, one would have liked to have the same images like XOS1s on both sides, but for data volume concerns and limitations, we went with the XOS2 design. There are other types of observation sequences that you might find. There's an XOS4, which is an excellent image in that the UV is still downsampled, but the visible are unbinned. So the idea was that these would make nice public outreach or public relations images. But these only happen once per week, so you can't really build a science campaign based on those. But they are there and they are in the archive. There are special calibration sequences. A common one you'll see is an XOS5 that has to do with using an internal lamp to measure the sensitivity, which is what we call the STIM lamp flat field. And there's also a fixed field gate test pattern that gives us some idea if there's some issue with the detector not related to the actual observing. Others are XOS15 we use for stellar calibrations, which is how we are keeping our radiometry so tight. And some that'll be popping up or starting actually next week in real time, but won't be in the archive for a while, are some special sequences that are high cadence imaging or high resolution. Next week or November 2nd, we're going to take an image that has 14 pairs of 320 in red images to look at cloud evolution. These are very special sequences, but I think that's an XOS6. We'll have a sequence like that during dust storm. For times when there's enough data availability, we can go in and look for some very interesting observations on occasion. You've heard a lot about these before, level 1, level 2, level 2A in the previous presentations. So these won't come as a surprise. I did see a question earlier and they answered about what's the difference between level 2A and 2B. There, you really should consult the data product guides. In our case, you'll only find level 2A at the moment. There is no A or B for our level 1. Level 2B will exist at some point, and that will involve map projections. That allows you to sort of align images that are taken not exactly at the same time, like all of them are, if the planet rotates or there's changes in distortion due to the camera optics. It puts everything together and lets you line them up on the same grid. Our level 2A is a calibrated product. In other words, we remove some of the instrumental effects from the level 1 images, which are not extreme in our case. You can almost use level 1 images for science effectively. When you look at the quick looks, you will see that they actually generally look quite good. I see there's a typo here. We do not scale our images to 80 bits. Our quick looks are 8 bits. Anyway, our level 2A products also contain the values of interest to analysis, the so-called backplanes, the photometric angles, the latitude and longitude, the sort of things that you actually need to do something with the image so you know what's going on in each pixel. And there are a few steps that are documented in the level 2A file, but you will find that in general, these are not extreme, at least by eye. File structures, Ryan's already talked about FITS files. I created this slide really for people to be able to access some more resources on their own. This is where you can go to learn about FITS, is that website. If you're more interested in sort of what are the definitions of the various components, there is the document from the working group. And that first link also has lots of information about FITS and ways to read things in. The EXI images use this concept of a header data unit. In other words, it's not a 3D cube in the level 2A, it's a series of 2D images for the most part. And there are some tables in there as well. So you have to access each 2D image separately to get the information. So that's what we're using here. And because these files get quite huge, when you get to level 2A, especially if it's floating point, we scale our data to 2 bytes so it compresses well. And this is within the FITS standard. It saves you room on your disk and a non-trivial amount. Integers definitely compress a lot better than floating point numbers. And although this is a lossy compression, anytime you take data and do this, you can never recover the original data, but it's so, the noise that's introduced is so far below the precision of EXI that there's no point. In other words, it's on the scale of 1/32,000. That is sort of the level of digitization noise. Well, roughly that, or 1/10,000 maybe. Okay, so a few more links if you're using this after the fact. And these FITS files can be read in many, many different ways. There's Python, there's standard interfaces for compiled languages, Perl, and then there are proprietary interfaces like MATLAB, IDL, etc. So there are definitely plenty of ways to access FITS files, and these will not be a mystery. And you can download things to work with them directly using viewers such as DS9 or FV. FV is a nice one that lets you directly access keyword values, explore planes. It's a little more extensive. DS9 is made more for visualizing, but both of them together, it sort of depends what you want. And there are many, many more. So the last link here is you can get a larger list of the software that's available both for reading and viewing at this URL. Okay, so diving into the meat, I guess I see we're almost out of time. These images are very basic. This is a level 1 image. This is the only case in which there's something in the primary image header. If you know FITS files, you'll know what I mean. It is technically an HDU, but it's not added on. The first thing you read is this image. We have other things like this data quality flag. If you look at that, that tells you which pixels we know are bad, in other words, you shouldn't believe them. And that gets propagated through the calibration process, as we'll see. These other two, the ancillary binary table and geocon, you really don't need to know about. And in fact, the geocon will disappear in the next release of these information or data to the archive. Well, here's just, so you can read it in very, very easily. You can see in Python, I was asked to kind of show an example at one point. It's not overly useful, except that when you read it in, you can tell exactly where in your structure that the Python module returns are the HDUs that you want. Here's a level 2A table. And again, but here the science image is in the first HDU after the primary. There's no image data associated with the primary header or the primary HDU. We have the data quality flag, which has now been updated to include uncertainties in calibration. In other words, if there's a bad flat field pixel, if there's something weird going on, or something that wasn't flagged in level 1 and is related to the products, it will show up in the level 2A data quality field. But okay, and so the ancillary data, again, you really don't care what that is for the most part. Geocon will disappear. Then we get into the things you might care about. There's a phase angle that tells you what's going on the pixel on the planet. There are the incidence angle, emergence angle. These are things you need to model the images. There are other useful information like the longitude and the latitude, look angles if you're getting to be sophisticated, like you want to look at the limb, height, if you're interested in the limb. These are things that might be useful if you want to go to the next level with using these images. But for the most part, they provide the photometric angles, the latitude and longitude, things that you need to model the data with the radiative transfer code yourself. So here's what it looks like. The same thing, you read it in and boom, there are all the headers that you want, and they're easily accessible in Python with structure notation. It's very nice to work with. You don't have to know where in the file is the height array. You know, is it the 9th, is it the 12th? There's no guarantee that these things are going to be written in this order, even though that is sort of the goal. That is why we use these HDUs that have names. Okay, perhaps more importantly, after you do the calibration, things are inserted. These are the radiometric coefficients, and you pull those out, and those can be used, as we'll see in a minute, to actually do a little more calibration. Fortunately, file names have already been covered, but they are very informative, and they were designed to allow you to do lots of sorting with regular expressions. One last concept to really bring up is this idea of a region of interest. The region of interest, to minimize the data brought down, we try to only take pixels around where we think the planet is going to be. And you can see the difference here in this image on the right. The white ones, those were pixels were not brought down to the spacecraft, but when the image is reassembled, they're filled with either blanks or not numbers, depending on your reader. So we capture the image, but we're not bringing a lot of extra data back so that we can actually bring more individual images back. And here's kind of what a quick look of that image looks like. So the quick look images are quite impressive in that you can really see a lot of stuff and could do some qualitative analysis. Closing practical comments. So here's basically the formula. You can turn the value that you get in a level 2A product into radiance and physical units with that formula. You can do it to irradiance, although irradiance flux, you just have to be careful, that's okay. These are really meant to be used on extended sources. If you actually, for some reason, wanted to use EXI images and you had a point source in the field, the level 2A products need some additional corrections, and that'll eventually be described in a document at the SDC. But maybe more importantly for what people want to do is a so-called radiance factor, or I/F. This is very commonly used in Mars science, whether it's atmosphere or surface-based. And there is a simple formula. It can be constructed from the DNs that you find in the level 2A image header and turned into the I/F just by using these various keywords in the header. And finally, the closing comments. I'm over a couple minutes here. Although the radiometric calibration is quite good, it should still be considered in work. And when we get updates, they will be a document that reflects that at the SDC and what the current versions are. The geometric calibration is not bad. In other words, how good is the latitude and longitude, or how good are they, or the photometric angles at any given pixel? Right now, it's within a few pixels. That's not a big deal for the photometric angles, but for the latitude and longitude, it's something we're still working on. It has to do with knowing how the optics distort the image onto the detector and being able to correct it precisely. So the things are good. We are updating our solar flux spectrum that's used so that we can, based on the, compared to the ones that were used to create the release data, and these will be replaced in the next data release, but it's only at a couple % level. It's not really something to worry about. But if for some reason you are, you can contact one of the SDC to get more information. I think in the sense that they'll pass you on to someone on the EXI team like me if you have a specific research question based on that solar flux value. But comparing those values to the updated values that I've been looking at, it's a couple % at most, most often less than 1 or 2%, less than 1% for the 320 bands. And even the 220 is not dramatically different. So in principle, the UV flux can vary. So we wanted to build that into the calibration. And finally, again, I mentioned several pixels in the geometry. These are in progress. And that is it for the presentation. Thank you.
Thank you very much, Mike, for the very informative presentation and for sharing those links. I'm definitely sure that that will be very helpful to share with the public as well to make use of. Just before we move to the final presentation, this is just to remind everyone once again that we will have a Q&A block by the end of the session where we will be answering your questions. So if you do get the chance and have the time to ask your questions, please do leave those in the Q&A box as well, and we'll be happy to answer those for you. And for now, we're going to have the last but not least presentation by Justin on the Emirates Mars ultraviolet spectrometer.
Okay, thank you, Moza. So my name is Justin Deegan. I'm the science lead for the EMU's instrument, and I'm at the Laboratory for Atmospheric and Space Physics at the University of Colorado. So I've heard a lot about the other two instruments. EMU's is an ultraviolet instrument, as its name implies. So it's looking at wavelengths that are very short, not quite X-rays, but much shorter than what we see with our eyes. And so the nominal wavelength range here is about 100 to 170 nanometers. It has a slit changer, so it's actually able to observe with different types of spectral resolution. And so the two most common of those are 1.3 nanometers and 1.8 nanometers. Those have corresponding fields of view that are 0.14 degrees and 0.20 degrees. So that will also affect, the spatial resolution that you have on the planet. Now, the instrument is designed to look both directly at the disk of Mars and look at various emissions from the disk. We'll talk about that a little bit more later, but also at the very faint exosphere that surrounds the planet. And so that's part of why there are these different observation modes that it has. So depending on how sensitive an observation you need and what kind of spatial resolution you need. It has a very sensitive detector. We'll talk in the next couple slides about how that works. So let's go ahead and do that. So EMU's field of view is a very long, skinny, what we call air glow slit. So here's a roughly to scale projection of what that looks like against the disk of Mars. And so how do you make an image of the planet with this? Well, if you just take one picture, so to speak, one integration with the instrument, what you get is this on the detector. So we're only looking at this little sliver on the planet, but we get with the instrument this image where the vertical axis here is that spatial dimension. We're looking at different locations along the planet's surface. Actually, we're not looking at the surface, we're looking at air glow coming from about 100 kilometers or so above the surface. But I've used a picture of Mars here that you could relate to better, just for illustration. On the other hand, on the horizontal axis here, what we're actually looking at is different colors, different wavelengths of light coming from the planet. And I've highlighted some of the more important ones here. Hessa mentioned hydrogen and oxygen. These are building blocks for water. We're interested in the evolution of water at Mars. We also see various bands coming from carbon monoxide, or CO. This is pretty common on Mars because Mars' atmosphere is predominantly CO2, carbon dioxide, but at the top of the atmosphere it gets split into oxygen and carbon monoxide by solar radiation. So we see signatures of all these emissions in the data that EMUS takes. There are a lot of other emissions blended in here that I haven't identified, and looking for those is getting into the field of spectroscopy. But we do see emissions from argon, diatomic nitrogen. We see other carbon monoxide bands. I'm not going to get into detail of that in this presentation. But, you know, one image like this is great. You could do a bunch of spectroscopy with it. But if you want to know what's happening across the planet, we need a little help from the spacecraft. So what typically happens is that the slit starts on a particular position of the planet, and then the spacecraft takes a picture and then moves the field of view. The instrument takes another picture, it moves, takes another picture. And so these integrations can be combined in order to build up images of the planet at a range of wavelengths. So the different regions that we're targeting with EMUs, broadly speaking, we're looking at the thermosphere. This is a region from about 100 to 200 kilometers on Mars where atoms and molecules are still collisional. They behave kind of like a gas that, you know, we would experience at room temperature. It's very, very thin, but it's still a collisional gas. And this is strongly heated by solar radiation. That's why it's called the thermosphere. It's very hot there relative to, say, the middle atmosphere of Mars. Now, above 200 kilometers, we have the exosphere, where the air is so thin that the molecules and atoms aren't really colliding anymore. They're just on Keplerian orbits, where they're just going around Mars. Maybe they'll come back down, or if they have enough energy, they'll go off into space and never come back. And that would constitute atmospheric escape. We further subdivided the exosphere into inner, middle, and outer regions based on how gravitationally bound the material there is. But the thermosphere-exosphere division is the most important one. And so in the thermosphere, we're looking for hydrogen, oxygen, and carbon monoxide. In the exosphere, we're looking at hydrogen and oxygen. Those are really the two main atoms that we find out there. So there are a number of observations to look at these different regions in different kinds of ways. And so I'm going to run quickly through the 4 nominal observation types that we have looking at Mars. So the so-called UOS1, U is for ultraviolet. This is observation strategy 1. We're looking at the disk of Mars. We like to look from the morning and the afternoon. So this little cartoon on the left, this diagram shows this position of the spacecraft as a square and an arrow showing which direction it's looking. Here's Mars with day and night side. And the view from the spacecraft for each of these looks something like this. So I have those exosphere and thermospheric regions identified and some little blocks here that represent scans of the instrument across the disk. And you can see over here, this is the kind of data that we get back. This is one of those oxygen emissions, and we can build a picture by taking those many integrations and stitching them together. So for this, we use the 1.3 nanometer slit and a fairly long integration. This allows us to do good spectroscopy and separate all those different emission features. The second observation strategy we have here, we're looking a little bit broader and we're looking from all around the orbit. So these OS2s, we're trying to characterize the 3D structure of the atomic hydrogen and oxygen in the inner corona. And so you can see here a different oxygen emission, and you can see I've really blown out the color scale here, but you can see that there's this broad emission away from the planet. And this is because there's hot, so-called hot oxygen that stretches out into space, and EMUs can see that. For this, we use a 1.8 nanometer slit. There are very few emissions in this in this region, the corona. and they're fairly well separated. So we can get a little more sensitivity at the cost of some spectral and spatial resolution, and that's fine. So the OS3 here also targets the corona, but here we're not looking for oxygen, we're looking only for hydrogen. And we take these at just a few places around the orbit, but we scan at very great distances. And so you can see in this data returned on the right that we can watch the hydrogen as it flows out into space. Hydrogen's the lightest atom, and it escapes pretty easily from Mars, and we're able to see that, the instrument. We do need to take background observations for these. These are these B-type observations. So the A-type observations are looking at Mars from either dawn or dusk terminator and the subsolar point. The background observations are necessary because there's hydrogen everywhere in the universe. And we only want to know, we're trying to separate out the hydrogen from Mars. And so we need to look away from the planet along the same line of sight in order to do that. And then we do a background subtraction. So be aware of that if you're going to work with this data set. The last nominal observation looking at Mars is OS4. Here, this is a very sensitive observation where we don't scan across the planet or across the corona. We just sit while the spacecraft is charging, and the instrument integrates for long periods of time. This is very, very sensitive. We're not trying to build a picture here. We're trying to see the faintest emissions from the corona, and we can build up profiles like on the right here for hydrogen and also oxygen. So these can occur on either side of the orbit, and there also are background observations associated with these, as shown in the diagram on the left. The last kind of nominal observation isn't looking at Mars. It's actually a set of calibration activities. I'm not going to go through these in detail, but these are ways that we make sure we understand the sensitivity of the instrument. Ultraviolet instruments are notorious for degrading in sensitivity over time, so we have lots of ways of keeping track of that and making sure that we're calibrating the instrument properly. One quick note is that in the data that's been released, we had some special data that we couldn't obtain in the nominal science orbit. So this is some special observations we took in that transition orbit that Hessa mentioned. When we're in that transition orbit, we got within about 1,000 kilometers of the surface, much closer than the nominal science orbit. And so we were able to take some limb scans. This gives us some vertical information of the air glow occurring in the 100 to 200 kilometer range that we couldn't get at any other time in the mission. So these are called CIS-15. That's just sort of a idiomatic name for this that came out during development, but all of the data is labeled that way. And if you're interested, you can download it right now. So I was going to finish by talking a little bit about the product format. So like the other instruments, EMU uses the FITS file format. I'm not going to go over this in detail because Brian already did that. But I wanted to point out two things that are unique to EMUs. One of these is the observation type. I just walked through all the different observations. So you can pretty easily search through the EMU's data for a particular type of observation that you might be interested in. And then those observations, many of them have multiple swaths where we scan back and forth across the planet. And so to make sure that you're getting all the data for a given observation, we have the swath number. So swath number X and Y. So in terms of the data products, at level 0, it's just packets. No one's ever going to look at that. It's really not human readable. At level 1, you can actually look at the detector images. A lot of stuff is uncalibrated and everything's not necessarily easily accessible for a human. Probably right now, you want to look at the 2A products. So these have calibrated detector images in those stacks of different integrations. We've also added geometry and pointing information for your convenience. Of course, you can always go do the SPICE calculations yourself with the kernels that are provided if you know how to do that. But we've tried to include useful geometry for all the pixels in the image. And so the HDUs that are in these level 2A files, there's a number of them here with the configuration of the instrument and engineering data and all sorts of things. Probably you want to focus for science on these latter few here, where we have a wavelength grid, we have the calibrated brightnesses, geometry associated with the position of the spacecraft, and the geometry associated with the field of view of the instrument for each integration. And so for those, for that geometric information in particular, we have a variety of parameters here. There's nuances depending on whether the line of sight intersects the airglow layer. We then report the geometry for a fictional surface at around 130 kilometers or so, which is roughly where the airglow comes from. If it doesn't intersect that layer, we have a different scheme for reporting the geometry. So all of this material is in the data product user guide, which is on the SDC right now. And so that's right here. We also have some spreadsheets with the level 1 product definition and the level 2 product definition if you want to dig in and find more information. So yeah, that's all live. So I'll end it there.
Thank you very much, Justin, for the informative presentation. Now that we've reached to the Q&A segment of this session, I just want to give some time for the attendees to leave their questions in the Q&A. Until we do receive some questions in the Q&A, I just want to go over some questions that were repeated by the attendees, just in case someone needs to know a few bit of information about what was asked. And there's no one specific to answer those questions, so feel free to just unmute your mics to answer those. The first question is the data free of charge?
Yes, Moaz, I can answer this. So all the data that is available in the Emirates Mars Mission Science Data Center is free and publicly available and can be used however a person wants to use them, whether that would be for research purposes or anything else. So there are no permissions required to use the data, no specific guidelines to use them as well.
Thank you very much, Hafsa, for responding to that. That was actually my next question about having permissions to make use of the data as well. So thank you for answering that. Another question that was brought up, not necessarily about the content, but about the session, was where they would be able to find the recording or basically get a hand of the slides. The recording of this session would be shared on the EMM website through a YouTube link as well, and you'll be notified on when that would be uploaded on the website. Other than that, if anyone would like to have the slides as well, you can leave your emails in the Q&A box as well. I'll take a note of that, and I'll be sure to send you those as well if you would like to have that. Now I'm just going to go through some of the questions here. There's nothing specific to be asked, so if the team does have anything that they want to share to the attendees within the last few minutes here, feel free to share that. Okay, if it looks like there are no questions at this point, then I think we can close off this session.
There is a question from Professor Murad Al-Shibli.
Yeah, I just saw it. There it is. Would it be, Professor Murad Al-Shibli asks, would it be beneficial to use AI and NN to analyze the data?
Are you asking us to answer now?
Yes.
Okay. The short answer is yes, but the longer answer is probably not. I mean, it's always useful and it's always interesting. The problem is to be able to come up with a training set for machine learning or even neural networks. You pretty much have to be a domain expert or be working with a domain expert, and you have to pick the problem so that it actually adds something. A lot of the models are actually pretty good for, say, doing retrievals in the lower atmosphere of properties. You know, I've often dreamed of having some computer do it for me so I wouldn't have to worry about it. But it's very difficult to do that sort of application at this point, because you have to have a good model to train it. And by the time you have a good model to train it, you could have solved the problem already. What is a possible application are identification tasks that the human eye sees. If you see dust and water ice, you look at a color image of Mars, and it's very obvious what's a water ice cloud and what's dust, because a dust cloud, so there's a lot of dust, not just thin dust. Clouds are white, and water ice clouds and dust clouds are orange. Now, it's a lot harder to program a computer to recognize that fact and tell you about the water ice cloud or tell you about the dust. So that is an application that probably works well, but so you have to choose carefully what tasks are actually appropriate to machine learning and neural networks. It'd be very exciting, but you got to pick the right one or you'll spend a lot of time and be frustrated.
Thank you for responding to that, Mike. Let's see what else we have. Is there, you can see people are typing some responses. If there's anyone else who has any questions, you can ask that in the Q&As.
I'll just chime in really quickly on the one that Mike is writing an answer to as well. I think the short version is that, we're always happy to collaborate and, work with you. And so if you have topics that you want to address, please feel free to reach out to the team, and we're more than happy to help you get, up and running with the data, or if you have specific questions about how to use the data, please don't hesitate to reach out and ask those. But as for being added to a paper, it's not explicitly required. If there's some material contribution that somebody does, that would be great. But at the same time, it's not required. And so I would say there are going to be a set of about 4 or 5 papers coming out in space science reviews that you heard each of us mention. And those are great places to start for references for giving the credit for, say, the instrument that you're using or the mission overall. And so that's where I would go to start first. And as additional papers come out, obviously there will be other ways to reference those as well.
Thank you for responding to that, Christopher. Just trying to see some questions here. Here's a question from Jawahar. I'm just sharing some questions out so you can just unmute and answer those if you wish to. Let's see. Is there a problem to solve in the UAV spacecraft to analyze data in space? And what could that problem be? I believe I asked that question the right way. Maybe not. Jawahar, if you could clarify that question, that would be good too. If I could ask that in a better way, probably. Let's see, there's another question by Yahakub. Just in case I pronounce your name incorrectly, I apologize for that. Has it affected any way the Hope Mars, basically the probe, while working recently, reported disorder conjunction in the solar system?
Sure, I can answer that as well. So during solar conjunction is a time period when the sun gets between the line of sight of Earth and Mars. And so we actually can't communicate with the spacecraft for a couple of weeks during that time period. And so the EMM spacecraft was put into a safe mode. So we didn't actually acquire data during that time, just to ensure that the spacecraft would be healthy and happy coming out of the other side of conjunction. That is the case. And so normal science operations will resume. I think all the instruments have been powered on again at this point, and the science operations should resume, I think, this week or early next.
Thank you, Christopher. I'm just trying to see any additional questions here. Another question is, what would happen to the Hope probe once the mission ends, by an anonymous attendee?
I can answer that, Moza. So we have our mission science phase duration is for 1 Martian year, which is 2 Earth years. Then we have the probe designed to operate for an additional 2 Earth years as well for an extended mission, given that we have funding for that as well. So we're still looking for more years of science and utilization for the probe, looking forward before we decide to end its life.
Thank you, Hassa. Just trying to see if there's any additional questions to address.
No, it will not crash into Mars. Actually, there are rules that we have agreed to as a team that are called planetary protection rules. And so as part of the design of the mission, we had to establish that, you know, at the end of life of the mission, it would not crash into Mars for a given period of time. And I can't remember exactly what period of time that was, but it's a really long time, like hundreds of years. And so the EMM orbit is actually a very, very stable orbit. And it does not take a lot of energy to remain in that orbit, which is very different than some of the other missions that you maybe have seen go to Mars, like some of these polar orbiting missions that are very close to the surface. Those take a lot of energy in comparison to EMM. So in all likelihood, EMM is going to remain around Mars for a very long time, even if it's off. So that's kind of a neat thing to think about.
Thank you for that, Christopher. Any additional questions? I'm just waiting to see if anyone else would like to type in their questions here.
I can maybe try Jawar's question as well. I think one of the things to think about when considering EMM data, and this is just kind of a broad answer, as compared to potentially some other data sets, like say a UAV, like the Mars helicopter associated with the Perseverance rover, is the scale of the measurements and how you link these measurements together. So the best way that I commonly think about EMM data is it's like a really sophisticated weather satellite that links what's going on in the lower atmosphere to how Mars loses its atmosphere and escape processes. And so we get this big global picture of Mars on relatively short timescales. But something like the helicopter or landers on the surface, you know, there are very localized things that you can do with those data sets. And of course, you can relate those back to EMM data, but that's not explicitly the job of EMM. EMM is trying to get this big overview picture so we can understand the broader Martian atmosphere. But you can use these individual locations as tie points, so like as ground truth to understanding what's going on. And sometimes, and I'll make this example for the thermal emission spectrometer, which is a precursor to EMIRS, and the mini thermal emission spectrometer, which were on board the Mars exploration rovers. One of our science co-i's, Mike Smith, and actually Mike Wolf, did some of this work where you could have a spacecraft, MRO or Mars Global Surveyor, looking down at the same time the rovers were taking data looking up with very similar instruments. And so you can actually get a different picture by doing that, looking up and looking down at the same time. And so that's one thing to think about as you kind of think about how these different observations work. You're not going to get a global view at one of these rover sites, but you can use the orbital data to expand upon what you can learn in detail at these landed sites.
Thank you, Christopher. I think we'll just take one last question from the anonymous attendee here. Is there a way any of the instruments can be used to study the ionosphere?
Yeah, I can take this one. So EMUS is sensitive to emissions from the region of the upper atmosphere where the ionosphere is located. There are a few ion emissions that are possible to see. There's a carbon plus, a couple of carbon plus emission features. There's an oxygen plus emission feature in the extreme ultraviolet that we have done some special observations during that CIS-15 data set. It's very faint, but we were able to detect it. However, those emissions are typically not actually telling you about the abundance of the ions in the ionosphere. Rather, they are what we call a prompt emission. They occur when the ion is created. So they're not so much telling you about an abundance of an ion. They're telling you a rate at which ions are being created, which is still useful information. That's about the extent off the top of my head of the information about the ionosphere that we have from the EMUS data set.
Thank you, Justin. I think we're good to close on today's session. Just for those who have any additional questions, I'll be sharing the science email in the chat for you to basically drop in any of your questions that you need any responses to. But other than that, I would like to thank the presenters for presenting their slides and sharing with us all those valuable information. And I would like to thank all the attendees for joining us today. So thank you everyone for your time.